Let's play around with the effective annual interest rate in Excel to understand the EAR concept and see the impact of the effective rate versus the nominal rate. Over here at the top of the Excel file, I have inserted the EAR formula as a text field. Then there's a section called Input Variables, which we can populate with various scenarios. Then a section with the output calculations, and at the bottom the various components of the EAR formula, so you can follow through step by step what happens to each element of the calculation. We are going to input the effective annual interest rate calculation as an Excel formula in cell B9. In the Home tab of Excel, go to Insert Functions over here and select the Power function. The dialog box now guides you through the steps. The number that we want to raise to a power is 1 plus I divided by n. In Excel you need to refer to the cells in which the data resides. 1 plus cell B4 divided by cell B5 to the power B5. Click OK and then add -1 to the calculation in cell B9 for the Excel formula to match the EAR formula in text at the top. Format the cell as a percentage with 2 decimals. I am displaying the EAR Excel formula in cell C9 for reference. Now let's see what's going on with the inputs and the outputs. At the nominal annual interest rate of 6% and 12 compounding periods, the effective annual interest rate is 6.17%. If the nominal annual interest rate is 6% and the effective annual interest rate is 6.17%, then the delta between the two is 0.17 percentage points or 17 basis points. If you apply that delta in interest rates to an amount of $10,000, then the additional amount of interest earned or paid is $16.78 per year. If we go to the components of the EAR formula, I divided by n is 0.5% in this example. The annual rate of 6% translates to a monthly rate of 0.5%. Cell B4 divided by cell B5. 1 plus I divided by n is 100.5%. Open parentheses 1 plus I divided by n, close parentheses, to the power n is 106.17% in this example. Deduct 1, which is equal to 100% from this, and you get the EAR of 6.17% in cell B9. We can now look at various scenarios of nominal interest rates and number of compounding periods. Let's start with changing the number of compounding periods. If the number of compounding periods is 1, then you are compounding annually, and the nominal annual interest rate equals the effective annual interest rate. If the number of compounding periods is 2, then you are compounding twice per year, every 6 months, which makes the effective annual interest rate slightly higher than the nominal annual interest rate. I divided by n is 3%, and 103% is raised to the power 2. The EAR is higher than the nominal rate once the number of compounding periods is higher than 1. In other words, more frequent compounding than annually. The EAR can also be lower than the nominal rate in case the number of compounding periods is lower than 1. In other words, less frequent compounding than annually, which is a rare occurrence in real life. If the number of compounding periods is 4, then you are compounding every quarter, every 3 months. I divided by n is 1.5%, and 101.5% is raised to the power 4. If we keep increasing the number of compounding periods, for example to 52, weekly compounding, then I divided by n keeps getting smaller, and the power to which this is raised keeps getting bigger. The incremental impact of more compounding periods in terms of EAR, delta in interest rates, or the dollar impact keeps getting smaller. What is very important to understand is that the delta between the effective and the nominal rate becomes bigger when the interest rate is higher and when compounding is more frequent, and the effect is not linear. 6% nominal annual interest rate compounded monthly makes the EAR 0.17 percentage points higher than the nominal rate. 24% nominal annual interest rate, a factor 4 increase versus the previous 6%, compounded monthly, makes the EAR 26.82%, which is 2.82 percentage points higher than the nominal rate, which is a factor of nearly 17x. At the nominal annual interest rate of 24%, the effect of going from monthly compounding, 12 compounding periods, to daily compounding, 365 compounding periods, is bigger than at 6% nominal annual interest rate. The EAR, based on a nominal rate of 24% and 365 compounding periods, is 27.11%. So beware of credit card debt with daily compounding. The great thing about Excel is that you can also calculate in the opposite direction, going from effective annual interest rate back to nominal annual interest rate. If the effective annual interest rate is maximized at 15%, then what is the nominal annual interest rate based on daily compounding? Click cell B9, then go to the Data tab, What If Analysis, Goal Seek. Set cell B9 to value 15% by changing cell B4. Click OK, and then let's display the nominal annual interest rate with 2 decimals. A nominal annual interest rate of 13.98%, compounded daily, equates to an effective annual interest rate of 15%.